afternoon, everyone. Welcome to Port Townsend Marine Science Center lecture series, The Future of Oceans. This is a remarkable turnout, and thank you so much for wading through whatever you waded through to get here. And it's going to be a great program. I'd like to begin by acknowledging that we work on the traditional tribal lands of many Coast Salish people, particularly the Slalom people, the Strong people. We respect and are grateful for this land, these waters, and the people who have inhabited them since time immemorial, and who continue to steward this place for future generations. I'd also like to acknowledge our sponsors for the series, the Darrow family, who make it possible for us to have this series of wonderful lectures all year long with no charge, so that everyone can come, and we really appreciate their support year after year, now in year 11. Thank you so much. Our speaker today is Eric McRae. This is that moment where like half the audience probably knows Eric, but if you don't, for those of you who don't, Eric went to school for degrees in electrical engineering with honors, and that was just the beginning. Since then, he's applied his problem-solving skills, knowledge, and significant creativity to a long career designing embedded hardware and software for systems in industries as varied as automotive, aeronautic, medical, autonomous underwater vehicles, and supercomputers. In 1991, he launched Electrologic Machines, his own systems engineering company, where he did a lot of those things I just mentioned. And then in 2011, he joined University of Washington's Applied Physics Lab, where he is currently a principal electrical engineer. In that capacity, he has been leading the design and operation of the Ocean Observatories Initiative's Regional Cabled Array Shallow Profilers. These machines operate autonomously in a vast internet-connected network for a year at a time, providing real-time data from the ocean floor through the water column to the sea-air surface that can be used for free. All the data can be used for free by scientists, students, policymakers, or really anyone with an internet connection. The OOI has enabled a new generation of underwater research for the past 10 years, and that's an entirely different talk that he's not going to give today. He's also a diver with a lifelong fascination in sound. Eric has worked on the Orca sound hydrophone network, which has a node here at Port Townsend underneath the pier where our aquarium is, and we use the archive of sounds from that system. And he currently volunteers for the Marine Science Center at our repair events with Jeffco Repair, which endears him to us even further. So thank you very much, Eric, for being here today, and please welcome Eric McRae.
Thank you, Diane. It's great to be here, and boy, what a turnout. I really appreciate this, and I appreciate the support that you all represent for the Marine Science Center. It was something that was near and dear to my life when I arrived in town in 1996 with two little girls, and we spent lots of time there, and over the years, between volunteering and watching them grow up to where they could reach into the touch tanks by themselves. It just was, it's been a wonderful experience for them, and of course, a wonderful experience for me to get to know the people of the Marine Science Center, and particularly now in these talks. I think these talks are wonderful. I was pretty excited to give this talk, and I was so excited that I decided to write a poem. So thank you all for being here, to learn from what you can hear. There are sounds that change your life, and there are sounds that you can't hear that are changing your life. The same is true for those in the blue. The same is true for our neighbors in the blue, those in the air and in the water too. So, thank you. That's all very good, but I think I'll keep my job as an engineer. So, we're going to talk about sound a little bit. So, what is sound? Sound basically is a brief variation in air pressure. And bear with me, we'll try to get down to the nitty-gritty details here, but air is mostly comprised of molecules of nitrogen and oxygen. There are some other ones, but those are the important ones for sound. And what you don't realize is there's bazillions of molecules in just a tiny little space. And so when we talk about these molecules, they're vibrating. They're always moving. In fact, the air temperature is based on the motion of these molecules, and they're bumping into each other. And it's a little bit like, if you can imagine this room just at the start of COVID, with no chairs in the room, you know the rule about staying 6 feet apart. So as people come in, everybody kind of moves away, and they jostle and sort of get as far away as they can from their neighbors. But people keep coming in and moving around. So the air molecules, it's a little bit like that. They're always bumping into each other. They're always moving. Sound is created when you get some sort of energy input that adds to that system. So if you imagine suddenly one of the walls moving forward 6 feet, everybody would crunch up, and then they would move back, and then the next people would move back, and the next people would move back. And that motion progressing on is basically what a sound wave is when you think of it in terms of the molecules in air. So you get it from mechanical input. You can also get it from heat input. That's a little harder to come up with an analogy for, but basically heat makes the air molecules move faster. They bang into each other faster, and if you apply heat suddenly to air, then you can get the same kind of pressure wave. The air wants to expand in the area of those hotter molecules and move away, and it creates kind of a wave as it goes away from the source of that heat. So here a region of higher pressure is formed. The molecules try to move towards lower pressure. They move away, but so they bump into their neighbors on the way. For all but extreme cases, the molecules actually don't move very far. So I'm nervous, so I haven't given one of these talks I haven't given any talk since 2016, so I'm a little nervous here. I'm going to light a candle, calm myself down, right? Thank you. So what I have up here is a special speaker called a subwoofer. It's a low-frequency speaker. You may have heard cars driving around with these. But I don't know if you can all see this candle, and you may not all be able to see this demonstration, but what I want to show to you, I'm going to turn on the subwoofer. It's at a very low frequency. Can you see the candle moving? So it's moving because the sound waves are going past it. Sound waves coming out of this, there's a little hole up here in the speaker, and it's causing that candle to shake. So I can stop it. Start it. Now, it's much harder to demonstrate if I went to higher frequencies, but the same thing is happening. Those are just pressure waves coming out from that speaker. I probably should blow this out. In case the fire department comes. So there's three kinds of sound I really want to talk about. Repeating tones. Tones is the first one. We're all pretty familiar with tones in terms of music, voice, machines, so forth. So this is kind of a diagram of a mechanical input over here. This wall is moving back and forth, a little bit like I said in the room full of people with trying to avoid COVID. As you can see, as it comes towards me, it creates a little wave. And that wave moves on, down, and it actually, as it moves back, it creates a little bit of a vacuum, so it actually evens things out. If you look, there's a couple, these represent air molecules, right? I hope that's clear. There's a couple drawn in red. You can see them. you can see that the red molecules are moving right and left, but they're not actually moving across, but yet the sound waves are still progressing. Same thing is true for a wave in the ocean. The actual molecules of water don't move far. They go in a circle, but the waves keep going. And the same is true in sound. Unless it's a very, very abrupt sound like an explosion or something, the individual molecules don't move very far at all. So that's just something to keep in mind. There's not wind. In other words, we can have that demo going over there, and I can stand here and I won't feel it at all. But the sound waves are still progressing past me. The characteristics of a tone are frequency, that's the most important one, or pitch, if we're talking about a pure tone, and amplitude, which is basically how loud it is. Humans generally can hear in the 20 hertz. Now, hertz is a name given for the frequency, the number of pressure waves per second. So 20 hertz means 20 pressure waves per second. A young person can hear all the way up to 20 kilohertz, 20,000 pressure waves a second. Adults, we tend to lose the upper range pretty fast. So I have a little experiment here, yet another one, and I'm going to make a tone. Some of you may hear this, some of you may not, but I'm going to set a tone that starts out at 5 kilohertz. Everybody hear that? So if you can hear this, what I'm going to do is, let me turn it down a second here. I'm going to raise the frequency. So when we start out, if you can hear it, keep your hand up, and as soon as you don't hear it, lower your hand. So we'll start out at 5. If you can hear it, raise your hand. Good. We'll go to 6, 7, 8, 9, 10, 11, 12. Now y'all look around the room. There's not too many hands up. 13, 14, 15, 16, 17, 18, 19, 20. No hands up. So it's just a demonstration of how we as humans, we're limited in our range. So the upper range, the highest person in here had their hand up at 19, I think, 19 kilohertz, 19,000 times a second. Dolphins can hear up to 70 kilohertz, and I think even higher. Just to give you, and bats are way up to 120 kilohertz. It's astonishing. We hear just like we only see part of the visual light spectrum, we only hear a small part of the audio spectrum, because there are sounds out there that are way above what we hear at 19 kilohertz. Typically, we call sounds that are above 20 kilohertz ultrasound, and you've heard of that for medical imaging. You may not have heard it. It can be used for welding, especially plastics. It's also used, there are a lot of cars that have backup sensors that are used to detect when you're getting too close, and they send out a signal that we can't hear, but it allows them to send out a signal and measure the distance basically to the car behind you or the bumper or whatever. If the sound is below 20 hertz, which we heard the sound that I was using here was 21, so it's very low. If below 20 hertz is called infrasound. Basically too low for most of us to hear. So infrasound occurs a little more rarely. We get atmospheric disturbance, sometimes the wind, you can get turbulence in the wind that'll cause a vibration that's very low frequency. A helicopter, sometimes a helicopter that has gone past you, the sound will actually drop, you'll hear it whoop, 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 whoop as it comes towards you. But as it goes away from you, you kind of don't hear the whoop, whoop, whoop anymore. One of the things we talk about a lot is the speed of sound. The speed of sound in air is not all that fast. It's pretty fast for us, but at 20 degrees C, room temperature, at sea level, the speed is 343 meters per second. If you don't know the meters kilogram system, well, I feel sorry for you. I want you to learn it, but but that amounts to about 4.5 seconds a mile. And one of the ways you can use that is you see a lightning flash and you start counting. And if you get to 1, you're lucky because it didn't hit you. If you get to 4.5, you know it's at least a mile away, and you can, keep counting. You can use 5 seconds if you're not really that concerned, but 4.5 seconds a mile basically is what the airspeed is at the ground. In the ocean, in saltwater, it's about 1,500 meters per second. So it's 4.5 times faster than in air. And in case you're encased in steel, the sound is 5,000 meters per second in steel. And the point here is that the denser the medium, the faster the sound. But we're going to concern ourselves mostly with air and seawater. One of the things that you, as an engineer, particularly you worry about is the wavelength of the sound. So what is that? That is, as the sound's traveling through the air, it's the distance between the pressure peaks. And as the sound gets higher and higher pitched, the distance gets shorter and shorter. So at 20 hertz, that sound that was wiggling the candle, the wavelength is 17 meters. So that means that as that thing is moving in and out, the other end of the sound wave is way over there. It's already hit the wall. But as you raise the frequency, so middle C on the piano at 440 hertz, the wavelength is only this far, 78 centimeters. And the higher you get, 2.5 kilohertz, it's about that much. And the pressure waves are that close together. So at that frequency, there's a whole bunch of pressure waves between, the source and, the wall. So there's another kind of sound. So we talked about tones. I'm going to talk about a shock wave. So a tone is a repeating series of pressure waves, but a shock wave is just a single wave going by. And when I was a kid, there was an Air Force base north of where I grew up in Michigan and one to the south, and they used to scoot back and forth, and we would periodically get these ba-booms as the sonic booms from the jets reached our home. And that happens when the jet is actually flying faster than sound can travel. So the sound waves actually build up into a pressure front, and it there's just one sudden significant increase in pressure, and it drops back to normal, and that's it. It's gone. You can also get a shock wave, of course, from an explosion. You can get it from lightning, where the lightning bolt superheats the air expands. As you remember, I said the heat energy will cause sound waves. The air expands, it'll send out a pressure wave. Turns out with lightning, it'll also do the opposite thing because the air cools down fast and you get a negative pressure wave too. But anyway, that's called a shock wave, just a single event. Third kind of sound is noise. Now, anybody who's had kids know what noise is, but I thought I'd play you just a little sample. There's something special about noise in which basically it's unlike a tone, which has a single frequency. Noise has all frequencies. So we get this going here. So that's noise. Sounds like rain, sounds like a shower head, steam coming out of a kettle. There's some interesting things about noise, and we'll get to it later because we're going to talk about a very specific case of noise audio, but it's just something I want you to be aware of, that there's tones, there's noise. And as long as we're talking about sound, one of the things we have to talk about is a measure of loudness. So one of the usual, measure we call a decibel. And there's a whole bunch of history behind that name that I'm not going to go into, but it starts out with 0 decibels is the softest sound a person can hear. And I looked around for actual definitions of that, and the only one I remember I read years and years ago, and forgive me, but it's the sound of a baby mouse peeing on an ink blotter 6 inches away from your ear. Pretty soft sound. Anyway, but if we get up, you can read these. I'm not going to read them all, but I'm talking to you probably somewhere between 60 and 65 decibels. Vacuum cleaner, 70. Pneumatic drill, if somebody's breaking concrete, is 90. A live rock concert, easily 110. Oh, easily it'd be more than that. But one of the things I want to note is once the sounds get that loud, they can become painful, and eventually they can become damaging. And just as sort of a side note, the damage is typically a combination of loudness and time. So it's all right, you can hear a bang that goes way above some of these, 130 decibels, as long as it goes away and you get to hear quiet for a while. But if you're listening to a rock concert for 4 hours above 110 dB, you may damage your ears. Okay, 120 dB thunder, 130 dB a passenger jet taking off 100 meters away. I hope that you're not near 100 meters away from a passenger jet taking off, but if you are, that's about how loud it is. So there's an interesting thing about sound. It can be bent. What I mean is the sound itself can't be bent, but its travel can be bent. You can focus it with things you can't see. So just like if you were taught physics in school, you know about refraction. Is you're looking into the river and you see a fish down there. The fish isn't really where you're looking. It's a little bit lower because the light is refracted by the change in density from air to water. But sound can be bent in a similar way, and the way that you get a density change in sound is by heating the air. Having a temperature difference will actually cause the sound to bend away from the warmer air. So I've had this experience, many of us have had the experience of being on a lake, some calm body of water, in the evening on a summer day, and hearing a conversation a half mile away on the other side of the lake. And it's kind of weird. You think about that. Normally it's hard to hear a conversation on the other side of the room, but you could easily hear people talking a great distance away as long as you're right near the surface of the lake. And the reason for that is the sound right at water level, or the air right at water level, is cool relative to the air above it. And so the sound that is starting at near the shoreline at the other side of the lake wants to work its way upward, but it's bent back towards the water by the warmer air. And of course, the water reflects the sound back up. So it just bounces back and forth between those layers, and then comes to you. Of course, anything you say goes to them. So remember that. But sound is easily bent by warmer air. So we as humans are pretty good at locating sound sources. And the way we do that is our brains and our neural system pays attention to the difference in arrival time for a sound that hits one ear versus the other ear. So if there's a sound on that side of the stage, this ear will hear it first, and then after the speed of sound, it'll arrive at this ear. Now, my ears are about 17 centimeters apart, and that means it's about 5,000ths of a second. If it's exactly that way, that this ear will hear it before this ear. And my brain can interpret that. It says, it's over there. We all do this. We do this without thinking. It's just part of our neural makeup. So what does it mean if a sound hits both my ears at the same time? Anybody volunteer?
It means you're facing the source of the sound.
Facing the source of the sound. In other words, it's coming right at me, so it hits both ears at once. Or it's behind me. coming at me. Either way, so anyway, that's, it's just something we do naturally. We hardly even think about it. We can locate a sound pretty well as long as it's somewhere out here or back there. This was made use of. This is 1930s era Dutch aircraft locator. So this person, this military man, had basically megaphones attached to his ears, and by just turning this way and that, he could turn until the sound sounded like it was the same level in both of his ears, and he could say the airplane is that way, even before he could see it. Now, what's missing here? What do you want to know with an airplane? There's two things. You'd like to know it's there, and you'd like to know, where is it vertically? And we as humans aren't very good at that. We hear a sound, we can know it's in front or behind, but it's a little harder. It's a lot harder for us to judge where it's coming from vertically. Owls can hear in 2 dimensions. So this is an owl skull, and you can see those are the nostrils. These big orbs here are for the big owl eyes, but you can see these are cavities that are hearing cavities. Their eardrums are inside their skull, and those paths are open to the eardrums. And see how asymmetric they are. This ear hears up, and this ear hears down. So when an owl is flying over a field, he's high up in the air and hears a screech. Not only does he know where it is right and left, but he knows how far forward and backward in one sound. Doesn't take any, they just know. So we can do that a little bit. So if you are ever trying to locate a sound, both vertically and horizontally at the same time, and I've had this with birds. I hear a bird, I'm in the woods, I hear a bird, I don't know. It sounds like it's up in the tree somewhere, I can't hear it. But if you take one hand, put it up here, and cup your fingers up like this, take this hand and cup your fingers down, you can do that. So you have to sort of center it this way and center it this way, and it usually helps to close your eyes so you're not distracted by anything, but you can actually get a pretty good sense of the vertical displacement to the sound source. So some mammals have this technique called echolocation. So we were just talking about location, but now we're talking about echolocation. And the way that works is the animal emits a sound and listens for where the echo comes back from. So if you are flying through the air, if you're a bat flying through the air, you can emit the sound, which to us sounds like clicks. I'll have a recording here in a second. And then if you hear an echo, you have some idea where the sound is coming from. And bats can also, their ears are asymmetric, they can also hear in 2 dimensions. So I'm going to play you a recording of bats, but bats do their sound in the ultrasound area, and you can't normally hear it. So the pitch of this has been dropped down artificially to our hearing level. But here we go. So listen carefully. We would interpret those as clicks. Now pretty soon he's going to start calling out to his mates. But those are high resolution echolocation. And I can't really get into the details of that, but the chirp is much better than just a click. It gives them much more information about whatever it is that the echo is coming back from. Orcas do the same thing, by the way. They actually chirp. So, sound in the ocean, which is obviously why a lot of you are here and why a lot of us live here. We like the ocean. We want to know about it. So sound in the ocean is pretty much the same as in the air, but sound travels faster underwater. Remember, it was 4.5 times faster than in air, and it travels farther underwater most of the time. So one of the things, I'm a diver, and the very first time that I went into the water, in the salt water, not in a swimming pool, I was stunned with how all the sounds that I was hearing, which were a great deal, sounded like they were right in the middle of my head. So why do you think that is? Anybody venture a guess? It's exactly right. It's too fast from between the ears. And remember, if in the air, if the sound arrives at my ears at the same time, I think it's like right in front of me. And that's basically all the sounds in the water arrive at either ear. It doesn't matter where the sound is. Your dive buddy can be right over there banging on his tank. And if you're not looking at him, you have no idea where the sound is coming from. It sounds like it's coming from right inside your head. And that is because we're not designed for listening underwater. But there are a lot of critters that are. We'll talk about those. One thing I want to cover is a special thing about sound. You remember I talked about the sound just above a lake being trapped. Well, it turns out that because sound travels faster in warmer water, and it travels faster in denser water. Remember that it travels faster in steel than in regular water. But so as you go deeper, even though you think that water is not compressible, it is actually slightly compressible. So in the ocean, as you get deeper and deeper, sound travels faster and faster, which means that sound that originates on the surface is actually bent back towards the surface. But the surface is warmer, so the sound is bent down away from the surface towards the cooler water. So there is this sort of region, and it's about, it varies depending on where you are in the ocean, but it's 1,200 feet, 800 meters. It varies, but there is, it's fairly deep. There is sort of a point of where the speeds equilibrate, and the sound wants to sort of stay centralized around that channel. And if it's off axis from that channel, it gets bent back towards that channel. And that's called the SOFAR channel. Sound fixing and ranging. It's kind of a bad acronym, but SOFAR I like because sound can travel thousands of kilometers in that channel if the sound is loud enough. So again, it's a little bit like above the lake, but it's going on below the water. So in 1960, there was an experiment done. Over here, just off the coast of Australia, there were a couple explosive charges set off at a known time, because this was a science experiment, and the sound traveled 19,820 kilometers over to Bermuda and was detected there. 3 hours and 43 minutes after the charges were detonated, they arrived over there. Now that's stunning. These aren't huge explosions. They were pretty good. They were 100-pound explosives, something like that. That the sound could travel in that SOFAR channel that distance. That's really something to think about. There are a lot of critters along that path that wondered just what in the heck happened. There's not too many, I don't know, we don't have any World War II veterans here probably, but sonar was a big thing and we've all heard it in the movies. Submarines used to send out, they would have this ping. I'll play one for you here. So here's a ping. You've all heard this, Jacques Cousteau or I don't know, somebody. And so the subs generated this sound in attempt to listen if there was anything else in the water within hearing distance that would return an echo. So if you were operating that sonar and you heard this, ooh, Anybody tell me what that means? So, what would you know from hearing that sound? Anybody give me a... Something's moving towards me. Now, why do you say that? The sound, it's pitched higher. Did everybody hear that? It's the echo is coming back at a different pitch. Okay, so I haven't talked about Doppler shift, and I'm not really going to get into the details, but basically if a sound source is coming towards you, emitting a tone, you hear it higher than the actual tone. So that means that there is something out there, and you said it's coming towards you, but we don't know. If we're in the sub, we might be moving towards it, and it might be sitting still. But nevertheless, what it means is the distance between you and that object is getting smaller. There is closure. What else? Is there anything else that you can infer from this? Distance. We know exactly how long it takes the echo to come back. So what that's measuring is the time from when we send out the signal till it hits something, is reflected, and travels all the way back. So we know what the speed of sound in water is. It's 1,500 meters a second. It actually took, I have some notes here, it took 2.9 seconds for the echo to come back. So half of that is 1.45 seconds. And at the speed of sound in water, that's about 2,000 meters. So we know whatever that thing is 2,000 meters away. If we're standing still, that raise in pitch means that thing is coming towards us. If we're moving, that means we're headed towards something that's not moving. And we only have 2,000 meters to make a choice, because it might be a mountain underwater or something. Anyway, that was basically the life of sonar engineers in World War II. And they could tell a great deal about some things about the echo, but what is missing? If you're in a submarine and you hear that, what is the one thing that's missing from that echo response? Direction, exactly. You don't know where it is. And so how might you calculate direction? So one of the ways is you could change the course of the sub and go off in a different direction and see how the conditions change. You know, if you turn around and went the other way, I don't want to get too into the details, but you can use geometry basically to actually locate where that thing is. So it's amazingly simple in some ways, and amazing how much information that could be extracted. So one of the things I said earlier was that sounds are, you talked about a positive pressure shock wave. You can have a negative pressure shock wave, and I happen to have a recording of one of those. This picture shows these yellow containers here are plastic covers over spherical glass balls, hollow glass balls, and they're used for flotation in science research at depth. Because when you get down near the bottom, these go down about 5,000 meters. When you get that deep, foam just gets crushed into nothing. I mean, it's always fun. We always paint faces on styrofoam cups and send them down, and they come back, about this big. All the normal things that you think of floating don't float at those kinds of pressures, but hollow glass spheres do most of the time. Yeah. So what you're going to hear is that this was done off of Hawaii. They had 17 of these lined up as a float to keep cables away from the instrumentation that was on the seafloor. And after several weeks of deployment, there was a defect in one of the glass balls, and it imploded. And when it imploded, that shock wave took out all of the neighboring glass balls. So all 17 imploded at once. And this is a recording made by a hydrophone that was not part of the system, so it's a little ways away. And I'll caution you, it may be a little loud, but I want you to Everybody be quiet. You'll hear the first bang, and then you're going to hear echoes after that. So, okay. So I'm not gonna, if you listen carefully to this recording, you can hear, I think, about 8. So what's happening there is the hydrophone was down at the seafloor, the glass balls were at the seafloor. The first bang was almost instant to the hydrophone, and then what you hear is the sound going up to the surface and then coming back down 5,000 meters each distance in that path. So it took it a long time for the echo to come back, and each time it comes back, it's spread out a little bit more, and spreads out a little bit more, and eventually, anyway, it was a horrifying sound to the scientists who had this instrument, but it's a fantastic recording showing acoustics in the ocean. But in that case, it wasn't an explosion outward. It was the seawater coming in and filling up the space that the glass balls had occupied. So, same thing, it's a sound wave, no matter which way it goes. So, let's talk about who uses sound in the ocean. We all know about whales and dolphins. We've seen all the movies and everything. There's lots of other critters that use sound. Herring, research has learned that herring in groups expel gas bubbles from their anus. And the scientists have called these fast, repetitive ticks, or farts. But they actually do that. They use it as a form of communication. And we don't really know at what level. It may just be, let's get out of here. I'm not sure what. I've seen seals and sea lions right off here hit the surface and slap their tails. Now, they're too far above the seafloor to be making a difference to the critters on the seafloor, but they're doing that for some purpose. They're communicating. And I'll have this book up here, but I want to reference a book by Amarina Kingdon, who lives in Victoria, actually. The book is called Sing Like Fish, and it covers a lot of what I'm talking about in terms of the ocean here. And in fact, it was a little discouraging to read it because I think, oh my gosh, this is everything I was going to talk about. But it's an excellent book. It's a little hard to read, but it's fantastic. Anyway, one of the things that is well known is fish have ears. People are around here aging fish all the time, looking at a little bone called an otolith, which is from a part of their hearing system. Now, in the case of fish, it's not, there's no eardrum, but there is this sensory organ that has little hair cells that can sense motion of fluid, and they can sense, not only are they vertical, or where they're going in water, but they can sense sound. Now, not all fish generate sound, but we know some do. Down in Florida, there's something called a frillfin goby, and the females locate their prospective male mates because the males make this grunting sound. Otherwise, their species doesn't survive without that form of communication. If you've lived on the East Coast, done any fishing, there's a fish called a drum. I have a recording of a black drum fish here. Let's see. And they're aptly named. So this is what it sounds like. Hear that boom. So they're using that. That's a mating call or something. I'm not actually sure. I'm not a fish biologist, but they're not doing that for fun. That's a form of their communication. One of the things I find super interesting is that there's been science that have studied coral larvae. So these are larval coral little baby corals. Now, the way corals are created is the adults are affixed to rocks on the seashore or reef or whatever, and they all of a sudden, have this big party, and all the gametes and sperm and everything goes out into the water, gets fertilized, and then these guys just drift away in the ocean currents. And the little baby corals, the little larvae, at some point realize they're big enough, and they need to find some rocks, and they're way out in the ocean. Well, it turns out that, all they have to swim with is cilia, little sort of hair-like cells on the outside of their shell. Not even a shell, really, outside of their, don't know what to call it. I'm not a biologist. But they swim towards the sound of a reef. And the experiments have done this by putting these things in a tank and having a reef sound sort of move around in the tank, and these little guys will swim towards that sound. Now that's amazing. You ever think of that? We don't think of, how sound is used by these things that we can hardly even see. But it is, in fact. And in fact, it's why they survive. So, I'm going to play a different sound for you here. Everybody hear that? We can join in. So, at the right time, you keep on, come on. At the right time in the summer at Alki Beach, you may hear this sound walking along the shoreline. Sounds just like this. In fact, this is 95 hertz, very close to it. The sound is coming from this guy, plain fin midshipman. So, thank you. Well, I'll turn this off. Normally they swim out in open water, but when it comes time to mate, the males swim into shore. They find a good place. They sort of burrow down in the sand, and they vibrate their air bladders at 95 hertz. And the females hear that sound and come to them. That's their elk bugle. That's their mating call. Looking for love at 95 hertz. Okay, so baleen whales that filter feed, basically, that grab large chunks of waters, sing. They don't do echolocation. We'll talk about whales that do echolocation, but just in case you haven't heard, I've got some recordings of humpbacks. These were made in Puget Sound. So these whales have songs. They may last up to 10 minutes, but basically it's a sequence of sounds that they make. I think they call them codas, and certain herds of whales will have their own sort of song. And this I find absolutely fascinating. There are humpback whale herds on both coasts of Australia, east and west coast. And they're distinct. They don't mix. They don't travel back and forth. But up until 1992, the whales on the west coast sang a different song from the whales on the east coast. But in 1992, 2 whales on the east coast started singing the west coast song. Now I say the whales don't travel back and forth, but surely they can hear their songs, just like you knew that explosion went all the way to Bermuda. In the right conditions, the whales can hear each other. But in 1992, 2 whales on the East Coast started singing that song. In 1997, more than half the whales on the East Coast were singing the West Coast song. And in 1998, the original East Coast song was gone. Now, I don't know about you, but when I was a kid, I learned a lot of songs that I don't sing anymore. And to me, it is just kind of astonishing that these whales decided, I like this song better, basically. It's cooler. I don't know. I'm not sure what their reasoning was. I don't want to anthropomorphize the whales, but for some reason, they changed their tune. They changed to that new song. Toothed whales, odontocetes, echolocate. So they are chasing food like salmon or seals or whatever, and they emit clicks, much like the bats do. Again, if you listen carefully, the clicks are actually chirps. You have to change the frequency, but they can emit chirps, and they have a special feature for generating sound. It's a melon. I'm going to hold it up here, but it's on top of their upper jaw, and they emit sound into that melon, which is special tissue, basically. And that tissue can focus the reflection of that sound forward out of the nose of the creature. And then the return echo comes and it's picked up underneath their lower jaw. And if you look at their skulls are asymmetric, just like owl skulls. There's a difference from right to left. So again, they can tell in 2 dimensions where that echo is coming back. So it's amazing. You just look at these guys and you don't really realize the technology that they've developed. And so one of the things to think about is, we as humans have been around for, 1 million years or something like that. These guys have been here for 50 million years. They've had time to learn a lot. I want to play for you, just in case you haven't heard. These guys, I can't imagine, but these are southern resident killer whales. This was recorded right here in Port Townsend. So there's calls. And if you keep listening, you'll hear clicks eventually here. You'll hear there's some more clicks. A little hard to hear the clicks, but there's clicks and calls going on there. And that's basically the clicks are they're locating food, or they may be navigating. They may be trying to say, how close is the seafloor, or how close is that other whale next to me. But and so between the clicks and the calls, it's pretty obvious these guys are really using sound to communicate, because they cannot see very far in our water, especially in the summer. It's pretty cloudy. So its sound is super important for the killer whales, and it's super important for dolphins. And as it turns out, it's important for a lot of the other creatures. Just as kind of a side note, the SETI Institute, who was originally famous for search for extraterrestrial intelligence, has a wing that is basically studying humpback whales. And they're taking thousands, all the recordings they can get of humpback whales, and sending them into I hate to use a term, but AI, artificial intelligence system, trying to detect where the information is in the songs and in the calls from the humpback whales. And their hope is, number one, that they will be able to somehow interpret the sound, and number two, maybe they'll be able to communicate back, be able to send a message back. I have a link. Take you to it when I get to the end of the talk here. You can look it up yourself. Of course, we need to talk a little bit about human disruption of the acoustic environment. For a long time, Humans have operated on the what we don't experience doesn't always concern us. We stand at the shoreline looking out at the water and we don't hear what's going on underwater, so we don't really pay much attention to it. But that's going to change. So ships, we see lots of ships going through the straits here, and I want to tell you, some of them make some awful noises. Ship noise, most of the ship noise comes from the propellers. It's called prop slap. There's a slight cavitation. It's like basically a creation of a vacuum bubble right at the leading edge of the propeller. And those occur and collapse and occur and collapse, and it really makes a lot of sound. And in fact, it's so powerful that it eventually damages propellers. And they have to be replaced and repaired. Engine noise gets transmitted through the hull. I got a recording of some ship noise here. Also, this was recorded at Port Townsend. Here we go. So this doesn't sound very loud, but this is a ship way out in the shipping channel. And if you're a diver in the water, this is a pretty loud sound. And not only is it loud at the frequencies I can hear, but I suspect it's super loud at the frequencies that the whales can hear. Now, we here in Port Townsend hear float planes all the time, flying back and forth between Seattle and Victoria. And it's an interesting study. They're not usually too bad. You hear a Doppler shift as the props are coming towards you, as they go past and so forth. Helicopters do it even more. You can hear the Doppler shift from the helicopters. One thing to note is the sound helicopters is louder below than it is above because the pressure waves are pushed downwards. That's what's holding the helicopter up, right? The Coast Guard helicopters are flying missions all up and down. Periodically, you'll see them by here. And if you get good, you can tell, long before you can see the helicopter, you can tell whether it's one of these dolphins coming from the Coast Guard or one of the other ambulance helicopters. In fact, for a while, there was one where one of the helicopter blades had some sort of defect, and it had a rhythm to it that was kind of fun to detect. So we have the jets. And I don't want to get into that argument about the jets, but I want to say a couple things. First of all, you don't hear a Doppler shift when a jet goes by. It's just loud, and it goes by and it stays like that. And the reason you don't hear the Doppler shift is because the noise coming from a jet is what's called white noise. It's every frequency. And every frequency shifted is still every frequency. So the Doppler shift has almost zero effect. So if you hadn't thought about that, next time one of those goes by, you say, oh, yeah, that doesn't change. It just stays loud. If you're on Whidbey, you don't hear as much sound as we do. One, because half the times the jets are coming right towards you, and jets coming towards you don't make so much noise. Whereas from Port Townsend, it doesn't matter. They're not coming towards us. They're crossing, and so we hear the sound all the way, whether they're coming or going. The other thing is that the sound, a great deal of the sound we hear here is reflected off the water. But if you're on Whidbey, there's forest around you. That sound that normally would be reflected is not. They don't hear that sound as much. So, if you run into somebody from Whidbey and they say, what's the problem? It's a different situation. One of the things I want to say is that those jets are loud. You remember the decibel scale ended at 130. These jets have been measured at 156 decibels, 100 feet away from their takeoff. That is a hugely loud noise. That's 100 times louder than the commercial jet aircraft. So they are loud. No, I'm not getting around it. They are loud. Fortunately, that sound in the air does not get into the water much. You can hear it, but not so much. So What have we learned about sound? Well, first of all, the most important thing is just variations in air pressure. We've learned that it can be reflected. We know it can bounce off things. We hear echoes. It can be refracted by density change, by air temperature and water. So that's something that we don't normally think about, but I want you to go out of here remembering that even thunder, sometimes we get echoes off clouds because they're cooler. So it's interesting. So, and then of course, remember it takes 4.5 seconds a mile in air, but only 9/10 of a second per mile underwater, so it's much faster. All sorts of ocean creatures use sound, not just the whales. Sound travels farther, faster underwater, and low frequencies. You didn't really learn this, but I'm telling you now, low frequencies go a long way underwater. As to the future, this is the Future of Oceans series. I have some predictions. Ships will become quieter. For environmental reasons, there will be environmental pressure from us, maybe, and economic reasons, because sound is energy wasted. Sound sent into the water. The military jets will go away. They'll be made obsolete by all sorts of other tactics. Small boats even will get quieter. If we're lucky, the gasoline-powered motors will get replaced by electric motors, which are generally quieter, and the hulls there'll be better design, there'll be much less turbulence, which makes noise. Quiet zones will be created, and this is kind of interesting. Quiet zones in the water. So this is U.S. Coast Guard District 13, which covers this area, 30 October 2024. Washington, Puget Sound, Admiralty Inlet, Quiet Sound 2024-25, voluntary commercial vessel slowdown at Admiralty Inlet in North Puget Sound. If you want to find this, look for Notice to Mariners. You can find this release. Basically, it's asking these ships to voluntarily slow down under certain conditions. And this has been done in other parts of the country, and it's making a big difference in the soundscape underwater. So I want to play one last little recording here, it's a little bit of a reach, but this is a mystery recording. Whoops. There, let's get this. So this is me. I made this sound, but I started with a natural sound. And what it kind of tells me, I kind of gave away the show there, but that sounds a little bit like some humpback whales singing. In fact, it sounds actually a lot like them in some cases. Is a western meadowlark. And my point there is that there's some commonality there. You got this great big creature singing. It sort of makes sense that it's a lower tone and everything, but it's still singing, just like the meadowlark. And maybe way back in time, those species have a common root that included that kind of communication. Anyway, my hope is that we learn a lot more about the life around us, and then maybe we will learn enough to communicate back. Who knows? So, Proust had a great saying, the only real voyage of discovery consists not in seeking new landscapes, but in having new eyes. And I've modified that a little bit for me. A different voyage of discovery consists not in seeking new sounds, but in having new ears. And with that, I have a slide here with some links. So if you look up this later, you can look at these links. Some of these were directly referenced in here. But basically, thank you for your attention, and I really appreciate that. And